All right, so we're going to start talking about the next type of reaction. So reminder on Tuesday, we spent most of the time talking about how things dissolve, ionic compounds especially, and we talked a little bit about polarity, and we ended talking about precipitation reactions, right? And a precipitation reaction was when you happen to make some combination of dissolved ions that doesn't stay dissolved. Turns out that's not the only time you can have a precipitation reaction where you have a solution and then you get a solid to form from the solution. For example, another solubility of most solids in most ionic compounds, their solubility in water goes up as the temperature goes up. You can dissolve more sugar in hot water than you can in cold water. You can dissolve more salt in hot water than you can in cold water, which creates some situations where you initially have a homogeneous solution at, say, 90 degrees Celsius, but when the temperature then drops, you wind up with some solid forming, or it stays oversaturated. They call supersaturated solution, which is an interesting phenomenon in itself. So those can also be considered precipitation reactions. When you start from a solution and then you change the conditions and a solid forms. But in the classic sense of the word, a precipitation reaction is that you mix two ionic solutions together and you make some combination that doesn't stay dissolved. All right, so what we're going to do today is we're going to talk about a little bit more about precipitation reactions, but then we're going to talk about pH and acid-base reactions, because that also is its own specific class of reactions that winds up being somewhat significant, especially in biochemistry, because it turns out most biochemistry is heavily pH dependent. Most reactions that happen in living systems can only happen if the pH is within a certain range. So as biochemical systems ourselves, it kind of is important to us to understand how that works if you're going anywhere into a STEM field, but especially into the biology, biochem realm. So we'll spend some time with pH in a little bit. So just a reminder, so that we have a slide on it, and just instead of just recording your notes, are three forms of writing out a precipitation reaction. The most standard way of writing it is your molecular equation. The problem with your molecular equation is it doesn't fully capture what's going on, because all of those aqueous ionic solutions, are really the ions separately dissolved. Right, so what you really have when you have lead 2 nitrate is you have lead 2 ions surrounded by water and nitrate surrounded by water. And then potassium iodide is really potassium ions surrounded by water and iodide surrounded by water. And if you don't form an actual solid, until you form a solid, they're all going to stay separated like that. And then our net ionic equation, basically anything that doesn't react just gets erased. If it's both a product and a reactant, you can cancel it out. It's once you have a balanced reaction, these balanced reactions are kind of like algebra expressions, where you can do anything as long as you do it to both sides. So if we have our total ionic equation, if we have 2 potassium ions on both products and reactants, we can just subtract 2 potassium from both sides. And as long as we do it evenly to the products and the reactants, it'll still be balanced. All right, so that's the gist of the net ionic equation, which is oftentimes just sort of a shorthand, where it doesn't matter what's paired up with these initially. What matters is that you have lead ions and iodide ions, and when they bump into each other, they stick together. And so then the way we evaluate this, whether or not things will precipitate, whether or not a precipitation reaction will happen, is by looking at these solubility rules. Right, and these are also sort of generalized, because it turns out everything is at least a little bit soluble in water. But these are good ballparks because there's a really, really wide range in what soluble means and what insoluble means. So things that are almost always soluble. Column 1 on the periodic table, ammonia, nitrates and acetates are pretty much always soluble. Chlorides, bromides, and iodides are pretty much always soluble with a few notable exceptions. Sulfates are mostly soluble except some similar exceptions. Things that are generally insoluble. Carbonates, sulfites, phosphates, hydroxides and oxides, and sulfides. Obviously, this is not an exhaustive list, right? There are polyatomic ions that are nowhere in here. Nowhere in here does it talk about chromate, for instance. So is chromate usually soluble or insoluble? Well, I don't even know off the top of my head. I would want to go double check before I committed to an answer. This is not the sort of thing you're going to have to memorize. Because especially in the day and age that we live in, where you all have a supercomputer that's linked to the sum of human knowledge in your pocket at all times, right? You've got a smartphone on you, you don't need to memorize this stuff. Literally, you might, if you're really paying attention, you might be able to tell where I grabbed this list from. It's from Wikipedia, right? Every textbook has its own version of this, and that's fine. They all mostly agree. And so use whatever form's available. So if we mix potassium carbonate and lead nitrate, do we form a solid?
Yes. Soluble.
Yes. So potassium carbonate is going to be soluble because potassium's in column 1, right? Potassium is soluble, no exceptions. Carbonates are generally insoluble, except group 1 in ammonia. So that makes us think we probably are going to make a solid. What would the solid be?
Carbonate. It would be a moss.
It'd be a carbonate. So K2CO3 aqueous plus PbNO3 2 aqueous. We know what these ratios are because we remember our polyatomic ion charges, right? This is why it was worth memorizing that list. When those react, there's 2 new combinations. We could have potassium nitrate, or we could have lead carbonate. Lead to carbonate is going to be solid. Carbonates are generally insoluble with a few exceptions. Lead's not one of those exceptions. So we're going to make lead to carbonate as a solid. Then what's left over? We still have the potassium and we still have the nitrate. And it's going to be aqueous. Because both of these are always soluble, no exceptions. So if we wanted to write this as the ionic form, total ionic form, we split everything up, right? Blow up each of these ionic aqueous compounds into its ions. If it's a solid, it stays together. What, in the interest of saving time, what would the net ionic equation be? Okay, so we might as well, since this is the first example we're doing today, we'll do the write it out the long way. 2 potassium aqueous plus carbonate aqueous. This is going to turn into lead 2. Then we have 2 nitrates aqueous. Our products then are gonna be lead 2 carbonate, solid, plus our 2 potassiums, still aqueous, plus 2 nitrates, still aqueous. There's our complete ionic equation, right? A total ionic equation. From here, if we want our net ionic equation, what do we have to cross off? What's on both sides? So potassium ions and potassium ions. Nitrates and nitrates. So then our net ionic equation is just carbonate ions aqueous plus lead 2 ions aqueous goes to lead 2 carbonate as a solid. I know I say this a lot, but there's no individual step that's that tricky, right? It's putting it all together, especially if I just give you this problem in a blank piece of paper. So if that's the case, what do? You take it one step at a time, one simple step at a time, or at least not overcomplicated step at a time. Right, everybody knows the saying about eating an elephant. How do you eat an elephant? One bite at a time, right? Don't make any individual step too tricky. All right, how about lithium sulfate and lead 2 acetate? So sulfates are mostly soluble. Lithium's soluble with everything except for phosphate. Acetates are soluble with everything, no exception. Oh, sorry. Silver is the exception. And even that's questionable because silver acetate is actually you can make a solution out of that. But sulfates are soluble with lead 2 as an exception. So we are going to make lead 2 sulfate as a solid. So we're writing that out. Li2SO4 aqueous plus Pb C2H3O2 2 aqueous reacts to form PbSO4 solid and lithium acetate. Aqueous and balance that we needed to there. If this all starts to feel really samey, it's because it is. The only thing that's tricky about it, not the only thing that's tricky, the only thing that's different about it, you got to check your solubility rules. Any of these, no reaction. Or any of the other two, no reaction. Copper 2 nitrate and magnesium sulfide. Is that going to make a product? Solid, I should say. Yeah. Yes, sulfides are generally insoluble. Copper is not one of the exceptions. So we're going to make copper sulfide as a product. What about D? Strontium nitrate and potassium iodide. Nitrates are soluble, no exceptions, right? So we know that potassium nitrate is not going to be a solid. What about strontium iodide? Iodides are listed as soluble with some exceptions. Strontium is not one of those exceptions. So when we mix these two solutions together, no noticeable change. No solid is going to form. We just have, if we tried to write the total or the total ionic equation, the products and the reactants would look the same. We'd have all the same ions floating around before and after. So we would just write NR for no reaction. All right, questions on precipitation reactions? We'll do a lab where we do a precipitation reaction, and I believe it's next week. Where we mix two solutions together, get a solid, filter it, dry it out, and weigh it to get a percent yield, like we talked about on Wednesday. So precipitation reactions are really commonly used for that. If you don't know how many moles you have of something in a solution, you just add something it's insoluble with to make a solid. Because once it's a solid, you can filter it out and weigh it. And if you know molecular weights, then we can work backwards from there to figure out how many moles we started with. That process is called gravimetric analysis. So I believe that's next week's lab. I mean, I guess I'm the teacher. I can decide it's next week's lab whenever I want, right? But I'm pretty sure that that's what we have planned. You might have noticed that I hedged when I said silver acetate. Silver acetate is listed here as being insoluble. Soluble versus insoluble, like I mentioned before, it's presented as though it's this binary state. It either dissolves or it doesn't. But as is a common theme, it's really more of a spectrum. All of these ionic compounds will dissolve in water at least a tiny bit. But when I say a tiny bit, I mean a really tiny bit. Some of these things that are insoluble in water, we're talking about, you know, when they're saturated, the molarity is 1 × 10⁻⁻15 moles per liter. At that point, within sig figs, we can basically say it's insoluble, right? But some of them are a little bit more in the middle range. Everything has a point where it becomes saturated. Even these compounds we say are soluble, right? So, for instance, sodium chloride. Sodium chloride, when you put it in water, you get sodium ions and chloride ions. But even that has a limit, right? We could say sodium chloride is soluble, but it's not infinitely soluble. If you just kept dumping more and more and more salt into water, what happens? Eventually it stops dissolving, right? It just sits at the bottom of the pan. Right? It turns out for salt in water, that's a pretty high number. I want to say it's something like 350 grams per liter. That's kind of a lot of salt when you think about it. That's almost a pound of salt for every liter of water. But it still has a limit, right? So to just say that things are soluble or insoluble is a little bit of an oversimplification. In fact, oh, where did that slide go? Let me pull up another slide real quick. Dropbox. There we go. Sometimes you get a solubility table instead of solubility rules. It's got a little bit more information in it, where it actually has the individual combinations. Instead of just saying phosphates are insoluble with these 4 exceptions, it actually lists things out. And sometimes they'll have more information, like slightly soluble. So we look at silver acetate. Silver's not, oh yeah, there it is. This one even has silver acetate listed as soluble, but it's slightly soluble. It's soluble to an extent, and that extent is a little bit less than, say, 350 grams per liter. Diego?
Why are some of these like blank? Why can't some of the compounds like?
It's a good question.
Doesn't exist.
It doesn't exist is the obvious example, but I can't think of a reason why magnesium sulfide wouldn't exist.
Yeah, that's.
So it could just be that they don't have enough data, or it's somewhere in that, do we say slightly soluble or do we say insoluble range? And so rather than come up, I mean, really, instead of even having 3 categories, it would make more sense if it was like, they just gave a number. And if you actually look up solubility tables online, some of them will actually just have numbers in each of these columns. And that number is either the grams per liter saturation point or the moles per liter saturation point. So magnesium sulfide might just be in that range where they didn't want to say soluble or slightly soluble, so they just left it blank. But again, Clean Scientific, they're a chemical supply company, so they might just mean that we don't sell it. Magnesium sulfide is going to be it's a mineral, if nothing else. Not for this one, for the lab that we're going to be doing next time. We do have a lab like that. We mix it together and see if a solid forms to develop your own version of the solubility table. I don't think that's one I had planned for next week, but again, I'm the teacher. I can do that if I want. Let me look at what I have. I think the example that the one that we have is you have a barium sulfate and you don't know what the concentration is, or you have an unknown sulfate and you don't know what the molecular weight is. I think it's that one.
Magnesium sulfide reacts with water.
There you go. So it's not soluble or insoluble. It's reacts with water. Yeah, because then you're going to make sulfates probably.
It reacts with water to make magnesium hydroxide and
Dihydrogen sulfide probably. That makes sense. So it's not that the compound doesn't exist, it's that it can't be dissolved in water. Slight difference, right? Some of these others I'm a little bit surprised by, because iron chloride and iron bromide and iron fluoride are all fine, but iron iodide apparently isn't. So chemistry is funny that way, especially when the d orbital's involved.
probably all hydro.
Yeah. All right. Let's go back to this slideshow. Any other question about precipitation reactions at this point? I know I didn't mention too that you can, even things that say insoluble, you can, by changing the conditions, get them to dissolve. For instance, this mercury 2 sulfide is a mineral called cinnabar. It's where the color cinnabar gets its name, or which is in turn where Pokemon got the name for Cinnabar Island. If you played the original Pokemon like I did when I was in junior high. Cinnabar is a mineral that dissolves in almost nothing. Both of these things are pretty much always insoluble. Mercury 2 is almost always insoluble with things. Sulfide's pretty much always insoluble. But if you put it in aqua regia, you can get it to dissolve and turn into mercury ions and sulfide ions. Sulfide ions then react to form sulfates. And there's a couple other things that happen to get it to dissolve. But I actually had a group in Gen Chem a few years ago who went out on a hike, found a cinnabar sample, brought it back to the lab. We made aqua regia. They dissolved it to make mercury 2 ions. And then we were able to make metallic mercury as a liquid metallic mercury as a product, starting from a mineral sample that they went out on a hike to find, which is kind of a fun process. It was very involved because this stuff is really stable. Bryce?
Did they purposely go out to look for that stuff?
Yes, in this case, they started that class with the idea that what they really wanted to do was take a mineral sample and make a metal sample from it. The easiest one to do would have been iron. Go out and find a red colored rock, and odds are high that it's an iron oxide ore. But then you have to use a blast furnace and smelt it down. And plus, iron is not nearly as cool as liquid mercury. That was the easiest process that they found with stuff. There's still some photography stores in some states that sell the chemicals for developing your own prints, that sell mercury ions, that you could take those and dissolve them and get metallic mercury from those. But you're almost certainly going to put yourself on a DEA watch list because you also use that for making meth. So that's why you have to go, like, you know, in the sketchy part of Carson City to find the right store that'll sell you that stuff. So there's a lot of us living in a border town. I say this a lot in my OChem class. There's a lot of stuff you can buy in Nevada that you can't buy in California, especially when it comes to organic solvents. We use a lot of organic solvents in OChem that they can't sell in hardware stores in California, but they can in Nevada. So we go over to the hardware store on Kingsbury and pick them up. Turns out California actually pays attention to what's really bad for the environment, at least sometimes, and less so in Nevada. All right, let's talk about acid reactions. So when we first talked about reaction types, we talked about acid and base reactions. What were the clues that we used to determine if something was an acid-base reaction? Hey, that's how we name them. Good. If we started with an acid and we don't end with an acid, there's a decent chance it's an acid-base reaction, right? But why? How do we define it in terms of nomenclature? Even how do we define an acid? How do we know if it's an acid or not? It's got hydrogens, right? Especially if you can look at it and say, okay, that looks like an anion, like nitrate that I know, and then it's just got enough H pluses to make it neutral. That was one of our first ways we can kind of identify. So we're going to name this as an acid. This is why we name them as an acid, is because of the second definition here. So all these came into use in different times. The Arrhenius definition was in the 1880s, so a while ago. Arrhenius, Svante Arrhenius. I don't actually speak Swedish, so I don't know if I'm pronouncing his name correctly, but I think it's a cool name, Svante. Svante Arrhenius first defined an acid as anything that when you dissolve it in water, it decreases the pH, or say it increases the concentration of H plus ions. Fun fact about Svante Arrhenius. He was also the first person to publish evidence that of anthropogenic climate change was a thing. In 1880, he had data. He was looking at all the reactions happening in the Industrial Revolution, and he started looking at all these numbers, all these coal burning factories. And he started saying, well, wait, if we do that, we're actually measurably increasing the amount of CO2 in the atmosphere. And even in 1880, they knew what a greenhouse gas was. So he actually ran the numbers and said, and predicted with a pretty high degree of accuracy, given this time, what CO2 global atmospheric CO2 concentrations would look like and corresponding temperature change would look like. The model that he published in the 1880s has only had to be tweaked slightly since then. So interestingly enough, it's not like that's a new conversation. He also thought that it might be a positive thing for humanity. I chalked that up to him partly to him being from Sweden and it being cold in Sweden. And historically, farmable land in the Nordic regions was at a premium because you couldn't farm all of Sweden just because of temperature and permafrost. So Rxns thought that that actually might be a positive thing because if we have more farmable land, we can produce food for more people. Should be less starvation. You know, he was missing some really important things like catastrophic weather events that come with this, because he was a chemist, not a meteorologist. All right, so back to his definition for an acid though. He just said anytime you increase the amount of H plus in a solution, that's an acid. Bronsted and Lowry were the two scientists who came up with the idea of calling something with an H plus that it can give away is an acid. So that's our most common definition. Well, now that we're used to thinking molecularly. And so that would have been probably in the early 1900s. They came up with that definition because once you start thinking at a molecular level and taking into account the nature of covalent bonds versus ionic bonds, they were the ones who were thinking molecularly. And then this last definition, Lewis acid, as an electron acceptor, that's sort of the opposite of Bronsted and Lowry. It's sort of like you flip the proton to electron, so you also flip donor to acceptor. And when I say proton donor, that's sort of shorthand for hydrogen ion. Because like we mentioned before, hydrogen ion has no electrons left, right? So if you have something like HCl, that hydrogen, if we treat this like it's an ionic bond, that H plus ion is just a nucleus floating around by itself, and it's a nucleus that has just a single proton in it. So we use that term of proton donor, it means something that can give away an H plus. And so that's where our nomenclature definition of an acid comes from. Something where you've got some H pluses it can give away. Then a Lewis acid just flips both of those things. So Lewis acid is anything that, if you have a proton donor, it has to be giving an H plus to something else. Whatever's accepting the H plus, it's kind of lending its electrons to something else. And this comes up a lot. I know it seems like everything comes back to, well, you'll see this again in organic chemistry. But it is actually true in this case. We use Lewis acids in organic synthesis a fair bit, because sometimes we want something to act as an acid, but we don't want to add H pluses. There are some reactions where if you add H pluses to the situation, you actually cause a different reaction entirely. So we have to avoid doing that, but we want to still put it into an acidic environment. So we use compounds that can accept electrons to stand in for a Bronsted-Lowry acid. All right, and generally speaking, an acid's going to meet at least two of these three definitions. They're all just different ways of looking at the same thing. If you put HCl as a gas and you dissolve it in water, it turns into H plus and Cl minus. So in that case, HCl is both giving away an H plus, so it's a proton donor, and it's also increasing the concentration of protons in the solution. So it's simultaneously an Rxns acid and a Bronsted-Lowry acid. And a lot of Lewis acids, like for instance, iron 3 is a Lewis acid because when you dissolve it in water, it'll actually make this complex with the water molecules where it basically makes it so that, excuse me, where the H pluses on a water molecule are not held to the water molecule as tightly. So you wind up making this structure that looks like this, surrounding the iron with hydroxides. And then you create a whole bunch of H pluses that are now free to move around. So basically you take a section of the water and you take all the oxygens from the water and they stick to the iron, which then leaves some of the protons free to move around. So this is a way that we can have something act as both an Arrhenius acid and a Lewis acid at the same time. But again, for the most part, we're not going to deal with Lewis acids in this class. Our standard definition for acids for all of this class and most classes is going to be Bronsted-Lowry acid, if it's got an H plus to give away. What's the other part of a reaction that involves an acid? It's not just an acid reaction, it's a... Who's got their notes from Monday when we did reaction types? That it was not just an acid reaction, we called it an acid-base reaction. So similar to redox reactions, you can't just have an oxidation or just have a reduction. You have to have something giving away electrons and something to accept the electrons. In the case of acids, you can't just have something giving away an H plus. You also have to have something that can accept the H plus. So the bases are basically the opposite of an acid. An Arrhenius base increases the concentration of hydroxide ions, which also means it decreases the concentration of H pluses. We'll talk about why in a minute. But a Bronsted-Lowry base, our standard definition, is going to be whatever the H plus goes to. If you put HCl in water, when you do so, when it acts as an acid, I know on the last slide I just had it written like this. It turns out you can't actually have just H pluses floating around by themselves. If hydrogen ions are floating around in water, they're going to react with that water. Hydrogen ions have a positive charge, right? So what part of a water molecule are they going to be attracted to? The oxygen. Think back to us talking about polarity, where we said, okay, well, water's got a partial positive here, and a partial negative here. If you put an H plus ion and floating around in water, it actually doesn't stay as an H plus ion. Basically, one of the lone pairs from the oxygen grabs it. It sticks to the oxygen, like throwing a tennis ball at Velcro. Like it just passes by, and then if it gets close enough, it just sticks there. So we don't actually have H pluses floating around when we dissolve HCl in water. When we dissolve an acid in water, we actually get the water reacting with it. And instead of making H pluses, we make H3O. Who remembers your polyatomics? H3O plus 1, which is also known as hydronium. Good. So in this case, in every case for this class, when you have an acid giving away an H plus, you have to have something to accept the H plus. So which of these two molecules is acting as an acid and which one's acting as a base? Water is going to be the base. Typically, the thing we name as an acid is going to act as the acid, but we'll see some cases where it doesn't have to be named as an acid. All right, so you will always have a pair when it comes to acid-base reaction. You can't have an acid reaction without a base reaction. What if the reaction happened backward? What would be the acid and what would be the base? If it was going like this, if you had hydronium and chloride, and it was gonna make water and HCl.
Yeah.
Yeah,
Nice.
it's the acid. If the hydronium is gonna be the acid, because it's the one giving away an H plus. It's a water molecule with an extra H plus. So it'll give away that extra H plus and act as the acid. The reaction, if the reaction happens backward, we actually have a term for these two things, the products of an acid-base reaction. Whatever gains the H plus is the base. If it happens backwards, it would be acting as an acid. So we call it the conjugate acid. So conjugate just means matched, basically. Not conjugate if you talk about like verbs in Spanish. But conjugate just means matched at its most basic. So a conjugate acid is the protonated form, is the version of the base after it gained the H plus, which would make chloride the conjugate base. All right, so anytime HCl acts as an acid, it makes the same conjugate base, which kind of makes sense. It's weird terms for it, but HCl, once it loses the H, is always going to turn into the same thing, right? So you wind up with these conjugate acid-base pairs where HCl turns into chloride, and H2O, when it acts as a base, turns into H3O plus. Right, so for the most part, I want you to be aware of these terms. And basically the way I will ask this on a test is, here's an acid-base reaction. Label the acid, label the base, label the conjugate acid and the conjugate base. But it's always going to be in the same general form. So let's put another example up there. So if we had ammonia plus bicarbonate, it'll react to make ammonium and what? If the ammonia gained an H plus, yeah, we get carbonate. So in this case, what's acting as the acid? Yeah, the hydrogen carbonate's acting as the acid, which means the ammonia is what? Base. What's our conjugate acid then? So whatever acts as the base turns into the conjugate acid. Whatever loses the H plus, we call this the deprotonated form. When it's lost the H plus, the deprotonated form is the conjugate base. Back when dubstep was popular, this led to a lot of really not interesting, they're pretty, we'll call them basic memes, but they're pretty funny about, you just drop acid on the ground, that's bad. If you drop base on the ground, that's bad. If you drop acid as you drop the base, that's a good time. I told you they weren't that good, huh? But these terms existed first. They're chemistry terms before they were pop culture terms. So we're gonna stick with the real definitions of them. Plus, that's misspelling base anyway. Right? I don't like misused homophones.
That's the only thing about it you don't like.
That's the main thing. That's the main thing about it I don't like. Who remembers how to name their acids? X, eights, ites. Eights turn into X. Ites turn into
Is.
us. Is. Ides turn into so hydrogen chloride turns into hydrochloric. So this is just a little bit of review since we're going to be talking about these acids again for a while. So again, this is why we had to memorize our polyatomic ions and why we had to do our nomenclature so that we can discuss these things quickly. What is that one? Dihydrogen sulfate, 8 turns to ic, so it's just sulfuric acid. DM? You're gonna get some funny looks. Put it that way. You're not technically wrong, but most people would not, most chemists would not call it that, especially since that's a really common one to use. Then you really get funny looks. If you go to the trouble to memorize that that's sulfate, then it's not that big of a step to go sulfuric acid, especially since this is one of the most important ones that we deal with. It's not a satisfying answer. The one that where it gets a little bit hazy is hydrogen chloride. Because if you remember back to our nomenclature packet, technically for it to be named as an acid, it also has to be dissolved in water. So this is hydrogen chloride. But this is hydrochloric acid. Really splitting hairs there a little bit. If you said hydrochloric acid gas, that again would not, you wouldn't be wrong. All right, so what would the acid-base reaction for carbonic acid reacting with sodium hydroxide look like? Try and write out that reaction. I'm telling you it's an acid-base reaction. It might be helpful to write it as in the ionic form instead of the molecular form. I'll give you a couple minute head start. Carbonic acid. Sodium hydroxide. Or we can split sodium hydroxide up into ionic form. What's going to act as the acid? What's going to act as the base?
Carbonic acid.
Makes a lot of sense that carbonic acid would act as the acid. We know carbonic acid's not really going to be able to act as a base because we can't really mean, I guess we could stick another H plus on it and get H3CO3 with a positive charge, but we've never seen anything like that before, right? In general, once you get your acids to neutral, you're not going to give them another H plus usually. So if this is going to be our acid, meaning it's going to give up an H plus. If this loses an H plus, what does it turn into? What's the conjugate base? So carbonic acid is going to turn into hydrogen carbonate. Then the question is, where does the H plus go? Is the H plus going to stick to a sodium?
Oh,
It's already positively charged, right? Trying to stick another positive charge on something that's already positive doesn't sound like a good idea. So if you have an H plus, it's going to stick to something that's negative, or something that at least has a negative, a partial negative. So it already has a hydrogen because oxide is so stable on its own, it won't dissolve in water. If you try to dissolve oxide in water, it steals an H plus from a water molecule. So we have, it's not that it already has an H plus, it's that it's got a negative charge. And if you're trying to give away an H plus, the obvious place to give it is to something that has a negative charge. Because positives are attracted to negatives. What do you get when you add an H plus to hydroxide?
water. Ooh, water.
The H makes it H2O. And it was a -1 charge and we added an H plus to it. So that makes the charge 0. And then we still have sodium. Nothing happened to the sodium, right? Poor sodium, it's floating around by itself. I just prefer to think of sodium as being satisfied, surrounded by water. It's not sad.
In this case, would the sodium be a spectator?
The sodium would be a spectator ion. Sodium is neither an acid or a base.
Like necessary for the reaction?
Yes, because you can't really add hydroxide to water without having a positive ion to balance out the charge. So it's not necessarily for the reaction, it's necessary to make the solution. Maddie? Yeah. So it's sodium because in this case, I said sodium hydroxide, but I could have said potassium hydroxide or calcium hydroxide. Calcium hydroxide would just change the stoichiometry a little bit because it's got a +2 charge. But other than that, yeah, that's fine. So sodium's a spectator ion. If we're writing the net reaction here, we could actually just cancel it, cross it out since it doesn't matter what it is. Which makes this the base, right? Hydroxide is one of the most common bases. Is conjugate acid or conjugate base?
Yeah. Conjugate base.
Conjugate base. Because if the reaction happened backwards, it would have to take an H plus from a water. Water is the conjugate acid. So there's a class of compounds that are called amphoteric, which means they could either act as an acid or a base. Hydrogen carbonate's another example. You take hydrogen carbonate and you have it act as a base, it turns into carbonic acid. But if you have it act as an acid, it turns into carbonate. So basically anything that's kind of in between having all of the H pluses and having no H pluses could be an acid or a base, depending on what you put it with. This is also why we use sodium bicarbonate is really, really heavily used as a safety measure in pretty much all labs, instructional or even research labs, Look next to the periodic table over there. That bag of baking soda. Baking soda is another word for sodium bicarbonate. Basically, if you spill an acid or if you spill a base, you just throw sodium bicarb on it until it stops bubbling. And then you'd be pretty safe. The other one that always gets weird looks is most labs have a like 5-pound bucket of cat litter laying around. As it turns out, if you spill something, cat litter is really good for getting it to clump together in a form where you could actually just grab it and pick it up and then put it in the chemical waste. If it's an acid or a base that we drop, we use the sodium bicarbonate and then we can just sweep it up or mop it up. But if it's something nasty, like a solution with mercury ions in it, we can just use cat litter and then we can treat it just with a, with a broom. We can clean it up and put it in the chemical waste. And if you live in the Midwest, everybody keeps cat litter in the back of their cars. Because it's actually really helpful because a lot of people in the Midwest don't drive 4-wheel drive cars, even if they live in a really cold area that has lots of snow and ice, because it's always flat. So if your car gets stuck in the middle of winter, you just throw some cat litter down that helps the ice melt a little bit and also gives your tires a little bit of purchase. Plus, if you're driving a rear-wheel drive car, putting a little bit of extra weight in the form of 20 pounds of cat litter is actually a really good way to help your car not get stuck in the first place. Cat litter, a multifaceted safety tool. All right, let's talk about pH. So, who here's heard of pH before? Everybody knows it has something to do with acidity, right? Generally speaking, it's just our normal way of measuring how acidic a solution is. Because it turns out how acidic or basic a solution is has a really wide range of concentrations. It actually would be better to just think about it in terms of hydronium concentration. Because however much hydronium concentration you have in an aqueous solution is a measure of how acidic it is. How much acid was dissolved in it in the first place. The problem with that is that your H3O plus concentration in an aqueous solution can go anywhere from about 10 to 10 to the minus 16. So since that's a really, really broad area, we use a log scale. So pH is just a log-based scale for talking about how much hydronium is around. So if you want to find the pH of a solution, you just need to find the hydronium concentration. If you find the hydronium concentration, you just take the log of that. Log base 10, not natural log. Which our calculators in the US distinguish. We use ln in log. If it just says log, that usually means log base 10 on a calculator, right? In engineering circles and internationally, if you just write log, it actually means natural log. So that doesn't matter a whole lot if you're going to stick to your American-made calculator. But if you use a search engine to do the math for you, especially Wolfram Alpha, you have to specify log base 10 when you type it in. Luckily, you can just type it in as log 10 of whatever. And it knows to interpret that as log base 10. All right, so by convention, if your concentration of hydronium is greater than a certain point, you get a pH under 7. If your pH is less than 7, that's how we define a solution as being acidic. If your pH is greater than 7, we call that solution basic or alkaline. What about a pH of 7? Water. That's another way to describe how acidic it is, though. If it's neither acidic nor neutral. Right, so if it happens to be a pH, and it gets a little bit more complicated of a definition, because it turns out the pH of a neutral solution depends a little bit on both what the solvent is and the temperature. But we'll get to that in a second. First off, though, a point here, because it's a log-based scale, if you change something by 1 pH unit, that's a factor of 10 difference. So if you go from a pH of 6 to a pH of 5, that's 10 times more acidic. If you go from a pH of 6 to a pH of 4, that's 100 times more acidic. Whatever your difference in pH is, 10 to that power. I don't know what just happened.
Sorry, I hit the clicker.
Oh,
That's what happened.
that makes a lot of sense. Sorry. Um. All right. If a solution is made of a strong acid, so how do we find the H3O plus concentration? It turns out that most solutions that we're going to deal with in this class are what are called strong acids. So who remembers what the definition of strong electrolyte versus weak electrolyte was? Completely reacts. We're going to use that. That means the same thing here. A strong acid means when you put it in water, it completely dissociates into H3O plus and the conjugate base. So HCl is a good example. HCl, when you put it in water, dissolves 100% into H3O plus and chloride. So if that's the case, what can we say about the concentration of H3O plus? What's it equal to? It's equal to our concentration of HCl. So if you want to know the pH of a solution, and it's a strong acid, as long as you know the concentration of the acid, you're good to go. For this solution, if the concentration of HCl is 0.15 molar, your concentration of hydronium is also 0.15 molar. So if we want to know the pH of that solution, so 0.15 molar. You just take the log of 0.15 and throw a negative on it. What do we get as an answer?
I got 0.8.
Good. Two things to pay attention to here. One is the units. When you take log of something that has units, basically the units disappear. So technically pH units are unitless. We just say pH units. Or we'll say pH equals 0.82. And saying pH equals counts as our units. That's the context for what that number means. The other thing that we've been dealing with a lot that's really a headache is what? Did we need to keep going past 0.82? Did the number keep going on your calculator? What do we do with sig figs? Turns out logs and exponents have a third rule for sig figs. So we've got multiplication and subtraction have their own rule for sig figs. Sorry, addition and subtraction have their own rule for sig figs. Multiplication and division have their own rule for sig figs. Logs and exponents have a third rule for sig figs that I'm not going to make you memorize. We're basically only gonna use log-based scales when it comes to pH. So we're just gonna set a blanket rule, which is for pH, you always go to the hundredths place. Don't worry about the sig figs past that. You just go to 2 decimal points. No matter how many sig figs you start with here, go to 2 decimal points. And no matter what's in front of the decimal point here. Basically, if you're actually interested in the rules, in the log rules, so basically anything to the left of the decimal point doesn't count as a sig fig. Because basically anything to the left of the decimal point is basically just what power is it to. It's like, if I said 1.5 times 10 to the minus 2, the minus 2 doesn't count as a sig fig, right? That's effectively what the number is in the tens and the ones place here. And so it doesn't count as a sig fig, only decimals count as sig figs. So, but again, I'm not going to grade you on sig figs when it comes to pH, just always go to the hundredths place. All right, how about the nitric acid example? 0.030. What is the pH of that solution? pH is equal to negative log base 10 of 0.030. pH equals right. I guess it would probably help also if you had a list of strong acids for this, right? Because this only works, this step here only works for strong acids. And there's, I want to say 7 of them. I always forget the 7th one. HCl, HBr, HI, HNO3, nitric acid, H2SO4, HClO4. I think the last one is HClO3. These are the big 6. And that one I'm pretty sure about. And the fact that they're a strong acid means that they dissociate 100%. So we can say this: whatever your concentration of your acid is equal to your concentration of H3O plus. And again, at this point, if I ask you the pH, it's pretty safe to assume I'm asking you about a strong acid. Because we haven't talked, it turns out weak acids, you can calculate the pH, but the math gets a little bit trickier. A little bit more interesting, I would say. So when we get into equilibrium, we'll talk about that briefly. But we're not there yet. Last example, what about sulfuric acid? H2SO4. If your concentration of H2SO4 is 0.010 molar, pH of 2. Because that's equal to our concentration of H3O plus. And negative log of 0.010 is 2. So pH equals 2.00. Still go to the hundredths place. Just always with pH for this class, go to the hundredths place. Does it matter that the sulfuric acid has 2 protons? Why not? It gives one away. It gives them away sequentially. So H2SO4 has 2 H pluses it can give up, but it doesn't give them up at the same time. And only the first one is strong. The second one is an equilibrium reaction that only dissociates some of the time. And we'll find out because it's a log-based scale, it basically that second proton is that is going to be given away some of the time. It's going to be an insignificant amount. It's get lost in the sig figs. So we can assume, even though it's got 2 H pluses to give up, it only gives up one and the other one stays attached for close enough to 100% of the time that we'll call it 100% of the time. It's actually like 99.99% of the time it stays attached. All right, last thing. Because there's nothing like the last 6 minutes on a Friday afternoon to cover a new topic. So we talked about acids in terms of H3O plus concentration. We talked about bases in terms of hydroxide concentration. Because it turns out those two numbers are related. They're related because if you actually put water in a solution of water, okay, if you had pure water, you actually have both an acid and a base present. Not strong acid, but water, we saw water act as an acid once, right? And we saw water act as a base once. So because water can be both an acid and a base, there's a certain percentage of the time that it acts as an acid and a base simultaneously. One water molecule will bump into another water molecule. One will give away an H plus and the other one will take it. Which means even if you have pure water, deionized water, nothing in it except water, you also have some hydronium and some hydroxide. What was the pH of a neutral solution? 7. How do you get, if your pH is 7, your pH is 7, and it's the negative log of hydronium concentration. That means you actually have some hydronium present. How do we solve for hydronium concentration if we know the pH? How do we go backwards from pH to concentration instead of the other way around? 10 to the power of both sides. Well, we want to move the negative over first. But then if we do 10 to the power of log 10 here, that cancels out. But we have to do that to both sides. So in a neutral solution, our concentration of H3O plus is not 0. It's 10 to the minus 7 moles per liter. So really small, right? 0.0000001 moles per liter, but it's not 0. That's why pH of a neutral solution is 0. And it's because these two numbers are inversely proportional to each other. When your hydronium concentration goes up, your hydroxide goes down. When your hydroxide concentration goes up, your hydronium concentration goes down. What that means is we can actually redefine this a little bit, where we have hydroxide or hydronium, it's written as H plus, but hydronium concentration times hydroxide concentration in water at room temperature, it's a lot of caveats there, is equal to 10 to the minus 14. Which if we take the negative log of both sides, we can get pH plus POH equals 14. So POH is just is basically like pH, except instead of talking about hydronium, we're talking about hydroxide, OH. Right, P is what's called in math is what's called an operator, which just means it's like a function. When you say P, it means take the negative log base 10 of something. So pH is take the negative log base 10 of hydronium concentration. POH is take the negative log base 10 of hydroxide. And what this also means is if we have the hydroxide concentration, we also have pH. So in a basic solution, you're not going to find pH by finding hydronium concentration because it's going to be a really, really small number. What you do instead is you find the hydroxide concentration and take the negative log of it. When you take the negative log of the hydroxide concentration, you get POH. And then you do 14 minus POH gives you pH. Right, so alkaline solutions have excess hydroxide, which means their pH is above 7. I know we're just about out of time. So none of this is on the quiz this weekend.
All right.
The quiz this weekend is a little bit, it's like balance the reaction, and then is this a redox reaction versus is this not a redox reaction? Right, so it's basically multiple choice. Go back to your notes from Monday and Tuesday. No problem. Have a good weekend.